Welcome back, math friends. This is AP Calculus section 2.6 notes. Today we are going to be talking all about tangent lines, slopes of tangent lines, equations of tangent lines, and how all these things are related to each other in terms of calculus. So we begin with discussing the slope of a tangent line. If we want to find an equation for a tangent line to a curve at a point P, we would start by taking a nearby point Q, and if you look at the picture here, here is my point P, and here is my point Q. And we could find the slope of this secant line, PQ. But as we start bringing Q closer and closer and closer to P, we're getting closer and closer and closer to the exact value of the slope of the tangent line at P. Recall that when we get closer and closer to a specific value in calculus, we call that a limit. So that brings us to this definition here, that the tangent line to the curve y equals f of x at the point P, which on our curve is some point x equals a, and then the function is f of a, is the line through P with the slope, the limit, as x approaches a, of f of x minus f of a over x minus a. And that is provided that this limit exists. And I want to put a little note here because we actually have two equations for slope in calculus. So this equation we are going to use when we have a specific point P where we want to find slope. And what I mean by this is we know the point P, like we know the point is 2, 5 or something like that. This is the equation that we're going to use when we know our point P, which brings me to the next part of the notes, which says that if we let that x minus a, which is underneath right here, which is in the denominator of our slope equation, if we let h represent x minus a, then x would be equal to a plus h. So we replace that f of x with f of a plus h, and we replace the x minus a with h. So all we've done is manipulate our equation a little bit, and now we have a new equation for slope. But the benefit of this equation is that it leaves our point in a generic form. So we would use this equation when we would like a generic equation for slope. At any point on our curve. So that's kind of the distinction between these two equations for slope here that we are given in our notes. So just to kind of illustrate the difference between the two of them, we're going to use both of them in example 1. Example 1 says find the slope of the tangent line to the curve y equals 4x minus x squared at point P, which is 1, 3, using both definitions above, and then find the equation of the tangent line at P and graph the curve and the tangent line. This is a very common problem in calculus. All right, so first I am going to use the equation m is equal to the limit as x approaches a of f of x minus f of a over x minus a. Okay, so that is going to be the first thing that I am going to do. So for our particular problem, m is going to be equal to the limit as x approaches. Now we have this point P up here, so 1 is our A and 3 is our f of A. So it's going to be the limit as x approaches 1 of f of x, that's just our function, so 4x minus x squared, minus f of A, which is 3, and this is divided by x minus A, so x minus 1. Okay, and now I need to do a little bit of work here. So I am going to rearrange my numerator so that my terms are in descending order. And I also notice right off the bat that my x squared is negative. So I'm actually going to factor out a -1 because it's going to make it easier for me when it comes to factoring my numerator. So if I factor out the -1, then I have x squared minus 4x plus 3 divided by x minus 1. And then that x squared minus 4x plus 3, I know I can factor. That's an easy factor. So that's going to factor into x minus 1 times x minus 3. And now I get to cross out those families of x minus 1 right here and right here. So then I have my slope is equal to the limit as x approaches 1 of -1 times x minus 3, which when I evaluate my limit, I'm plugging in 1 for x, so my slope is going to be -1 times 1 minus 3. 1 minus 3 is -2. -2 times -1 is 2. So I get that the slope at point P is 2. The next thing we're going to do is we're going to find the slope using the secant equation. So this time we're going to use m is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. All right, and this one is always more work, just so you know. So this one, we're going to have m equals the limit as h approaches 0. F of a plus h means that we are plugging a plus h in for our variable x wherever it appears in our equation. So 4 times a plus h minus the quantity a plus h squared. That's my f of a plus h minus f of a, which is going to be minus 4a minus a squared. And this is all divided by h. Now I have some simplifying to do. M is equal to the limit as h approaches 0 of 4a plus 4h. And then I have a plus h quantity squared, which is a FOIL. That's going to give me a squared plus 2ah plus h squared. But the negative in front gets distributed to all three terms. So it's going to be minus a squared minus 2ah minus h squared. And then finally distributing the negative into the bracket there, we're going to have minus 4a and plus a squared. And again, this is all over h. So now notice in my numerator, I have some terms that I'm going to be able to cancel out. I have a positive 4a and a negative 4a. I have a positive a squared and a negative a squared. So then what I have left is m equals the limit as h approaches 0 of 4h minus 2ah minus h squared all divided by h. I still can't evaluate my limit because I'm supposed to plug in h equals 0 and I still have that h in the denominator. But notice that I have that factor of h in all three terms of my numerator, so I can factor it out. So this will be the limit as h approaches 0 of h times 4 minus 2a minus h over h. And now I get to cross out the h's, and now I can evaluate my limit by plugging in h equals 0. So m is equal to 4 minus 2a minus 0. which just gives me m equals 4 minus 2a. Now, this gives us an equation for slope at any point x equals a on our curve, which is very useful if we wanted to find the slope of the tangent line at multiple locations on our curve. But for this particular problem, when a equals 1, my slope is going to be 4 minus 2 times 1, which means my slope is going to be 2, which is the same answer that I got using the first equation. That should always be true. All right, so now that I know that my slope is 2, it's time to write the equation of our tangent line. And we know from Algebra 1 that to write an equation of a line, we need a slope and a point so that we can do point-slope form. Well, now we know our slope is m equals 2, and we know our point, which is our a f of a, and that is the point 1, 3. So now we do point-slope form, which is y minus y1 equals m times x minus x1. So we have y minus 3 equals 2 times x minus 1. On this side, we're going to get 2x minus 2, but then when we add the 3 over from the other side, we're going to get 2x plus 1. So there is the equation of our tangent line. Now, the last thing that we are asked to do is graph both our function and our tangent line and show that the work that we've done here is correct work. All right, so my function was y equals 4x minus x squared. So if I just make a quick table of my fave 5, and see where that gets me. If I plug in negative 2, let's see here, 4 times negative 2 is negative 8. And then negative 2 squared is 4. Negative 8 minus 4, this is going to be negative 12. When I plug in negative 1, I get negative 4 minus 1, which is negative 5. When I plug in 0, I get 0. When I plug in 1, I get 4 minus 1, which is 3. When I plug in 2, I get 8 minus 4, which is 4. All right, I'm going to throw one more on there. When I plug in 3, I get 12 minus 9, which is 3. So it looks like this is where my table starts to repeat. So it looks like for my parabola, my vertex is actually right here at 2, 4. And then I have a point at 1, 3, and I have a point at 3, 3. And I have a point at 0, 0. So I would also have a point at 4, 0. And then negative 1, negative 5 would be down here. And I would have a point across over here. All right, so there's my parabola. Now let's sketch our tangent line. And our tangent line was y equals 2x plus 1, y-intercept of 1, slope up to right 1. There's my point P, up to right 1, down to left 1. So there is the equation of the line tangent to the curve at the point P. A common topic in AP Calculus is velocity. If an object's position is described by the function f of t, or f of x, but f of t because it's based on time, then in the time interval from t equals a to some other point t equals a plus h, the object's change in position would be wherever it's ending minus wherever it's beginning, right? And the average velocity over this time interval would be its displacement. That's its f of a plus h minus f of a, the distance that it traveled, divided by the time. And for our purposes, this is f of a plus h minus f of a divided by h. Notice that this is the same equation as the slope of the secant line that we were just working with in the previous problem. And if we compute that average velocity over shorter and shorter periods of time, remember, as we bring that point Q closer and closer to that point P, we are calculating the limit of these velocities, which we call in calculus instantaneous velocity. So the velocity at point P is instantaneous velocity. The velocity between point P and point Q is average velocity. So V of A is equal to the limit as h approaches 0 of f of A plus h minus f of A divided by h. This means that the velocity at time t equals A is equal to the slope of the tangent line at P. A very important relationship to understand. In our next example, it says that a rock is thrown upward on the planet Mars with a velocity of 10 meters per second, and its height in meters after t seconds is given by h equals 10t minus 1.86 t squared. All right, so I just want to, before we do any math here, I just want to sketch a little picture of what this would look like. If we are on Mars and we are throwing a rock upwards, first of all, our entire graph is going to be happening in the first quadrant. And whenever you throw something up and it comes back down, mathematically speaking, this makes a parabola shape. Sorry, that should be a perfect parabola. Okay, where this axis, our x-axis, is going to be our time, and in this case, they told us time was in seconds. And this axis over here is going to be our height, which they told us was in meters. And this parabola represents the function h of t is equal to 10t minus 1.86 t squared. Okay, so this function gives us the height of the rock that we threw after any t number of seconds. We would just have to plug t in. So if we are talking about the velocity of the rock, then v of t at any time t is the slope of the tangent line to the curve at any time t. Okay. So if we look at what they are asking us to do in this problem, they want us to find the velocity of the rock after 1 second. So that is when t equals 1. Part B, they want us to find the velocity of the rock when t equals a, so after a seconds. That's where they want us to find that generic equation for velocity. So part A and part B, what they're really asking us to do is use those two different equations for the slope of the tangent line or for the instantaneous velocity that we learned earlier in this section. One of them is when you know your point, and the other one is when you don't know your point. And then part C, when will the rock hit the surface? Well, that's asking us when will the height of the rock be 0? And then finally part D, with what velocity will the rock hit the surface? Well, that's going to combine together the time it takes for the rock to hit the surface with the velocity equation. So let's start with part B, okay? And here's why. Let's write a little note so that when we come back and look at this later, we understand why. So note, we are asked to find velocity when t equals 1 and when t equals a. It makes more sense to do part B first. okay? Then we can use the result from part B to find part A. All right, so I am going to start with part B, okay? And part B, I'm going to be using my equation that v of A is going to be equal to the limit as h approaches 0 of f of A plus h minus f of A over h. Okay, that's just the equation that I'm going to be using. But I'm obviously going to be using my function that I was given in this problem. So v of A is going to be equal to the limit as h approaches 0 of 10 times A plus h minus 1.86 times A plus h squared, and then minus my f of A, so minus 10A minus 1.86A squared. And this is all divided by h. All right, so now I have some simplifying to do. This is going to be equal to the limit as h approaches 0 of 10A plus 10h. A plus h quantity squared is a squared plus 2ah plus h squared. And then when I multiply that negative 1.86 through, I get negative 1.86a squared minus 3.72ah minus 1.86h squared, and then minus 10a and plus 1.86a squared. And again, this is all divided by h. Now I can cross out the terms that are going to cancel. I've got a 10a and a negative 10a. I have a negative 1.86h squared. Oops. Sorry. That is supposed to stay. Crossed out the wrong one there, sorry. Got to keep my h squared. Negative 1.86a squared and positive 1.86a squared. And so now all of my remaining terms have the h in them, just like before. So I'm going to be able to factor that h out. So I have v of A is equal to the limit as h approaches 0. And again, I'm just going to take these remaining terms and I'm going to factor an h out. So it'll be h times 10 minus 3.72a minus 1.86h, and this is all over h. So then I can go ahead and cancel my h's. And when I do the limit as h approaches 0, I get v of A is equal to 10 minus 3.72a minus 1.86 times 0. So that term just cancels. So v of A is equal to 10 minus 3.72a. So this gives me an equation for the velocity of my rock anywhere at any point t equals a on my curve, okay, which is useful because if I wanted to find the velocity when t equals 1, when t equals 2, when t equals 5, I would definitely want to just find this equation, and then I could just plug those different values in for A. But now, part A, so I'm going back to part A now, part A asked me to find the velocity of the rock when t was, or after t equals 1 second. So for part A, when t equals 1, then I'm going to use my equation. It's going to be v of 1 is equal to 10 minus 3.72 times 1, which when I do the math, the velocity after 1 second is equal to 6.28 meters per second. Part C is asking me to figure out when will the rock hit the surface. Okay, the rock will hit the surface when the height equals 0. So first, we have to figure out when that happens. Well, we have an equation for height, right? The equation that we're given for this problem was h of t is equal to 10t minus 1.86 t squared. So if I set that equal to 0, that's when the rock's going to be on the ground, when the height of the rock is 0. And I can factor a t out. So t times 10 minus 1.86 t. And if I use the zero product property, that tells me that the height of the rock is 0 at time 0, right before we throw it. That makes sense. And then if I say 10 minus 1.86 t is equal to 0, and I solve that for t, that's going to give me t equals 5.376 seconds. All right, so that's when the rock will hit the surface, after 5.376 seconds. Part D of the problem is asking me with what velocity will the rock hit the surface? Well, in order to find the velocity when the rock hits the surface, we need to find v of 5.376. Well, that's easy enough. We just take our velocity equation and we do v of 5.376, which is equal to 10 minus 3.72 times 5.376. We do the math, and we get negative 9.99 meters per second. So that tells us that the rock hits the surface with a velocity of almost negative 10 meters per second. We just completed example 2, where we had our problem with our rock being thrown upward on the planet Mars, and we had a height function in meters. And we discovered that when we found the rate of change of the position of the rock, we were able to find the velocity of the rock. In general, if we have some quantity y that depends on another quantity x, some mathematical relationship where we have a function that represents that input getting plugged in and then becoming an output, we could use this different quotient to find the average rate of change between 2 points on the function. And the picture here on the right-hand side illustrates this. Here we have our points P and Q again. And the idea is that as we bring that point Q closer and closer to that point P, when we're finding the slope of the line between P and Q, it's a secant line. But as Q inches closer and closer to P, that secant line gets closer and closer and closer to the tangent line at P. And so when we take the limit of those slopes, we are actually finding the tangent line at P, which is the average rate of change of the function at point P. Now, it was nice in the previous problem we were given a function. But what if we're not given a function? And what if we're just given some information that is supposed to be represented by some function and they still want us to find a rate of change? Well, we can't find the exact tangent line at P if we don't have a function, but we can certainly do a good job of averaging it. If we look at example 3, it says the number n of U.S. cellular phone subscribers in millions is shown in the table with mid-year estimates given. So we have the years 96, 98, 2000, 2002, 2004, and 2006, and the number of subscribers at the middle of each year. Part A asks us to find the average rate of cell phone growth. Well, we know that that rate of change is going to come from finding the slope between the given years. So for letter A, part 1, the first thing that I'm going to do is I'm going to find the slope from 2002 to 2006. So I'm going to be looking at these two ordered pairs. And my slope here, so I will call this 2002 to 2006. My slope is going to be equal to 233 minus 141 divided by 2006 minus 2002, which you grab your calculator, that gives you a slope of 23, and they want us to include the units. Well, remember, our numerators are our phone subscribers, and our denominator is years. So our units here for our rate of change between these 2 years is going to be subscribers per year. The second one asks us to find the rate of change from 2002 to 2004. So looking at these two ordered pairs, my slope here is going to be 182 minus 141 divided by 2004 minus 2002, which gives me a slope of 20.5 subscribers per year. And part 3 of letter A asks us to do 2000 to 2002. So these two ordered pairs. So my last slope here is going to be 141 minus 109 divided by 2002 minus 2000, which gives me a slope of 16 subscribers per year. And again, the best that we could do here was estimate our rate of change using the data in the table, because we don't have a function to be able to plug into one of our slope formulas to find the exact value. Letter B says estimate the instantaneous rate of growth in 2002 by taking the average of 2 average rates of change. What are its units? Okay, so in calculus terms, in part A, we were finding the slopes of the secant lines. If we had graphed all of these points in our table, we found the slope between the point where x was 2002 and 2006, that's a secant line. We found the slope between 2002 and 2004, and we found the slope between 2000 and 2002, 3 different secant lines. Well, now they're asking us to find the instantaneous rate of growth in 2002. So they're really asking us, what is the slope when t is 2002? But again, since we don't have a formula, the best thing that we can do is work with the information that we have. So it makes sense in this case that we would use the 2 slopes to average together that are closest to 2002, which would be the slope from 2000 to 2002, that was number 3, and the slope from 2002 to 2004, that was letter 2. So I'm going to take these 2 slopes for letter B, and I am going to average them together to estimate my instantaneous rate of growth in 2002. And my slope average is going to be equal to 20.5 plus 16 divided by 2, which gives me an estimate instantaneous rate of change of 18.25 subscribers per year.